It's my pleasure to welcome you on the last talk before the party. So I'm also waiting for it. However, I promise you, you will have at least mildly good time. My name is Artur Skowron, and I'm a head of Java Kotlin developer in the Virtus Lab company. If you ever heard about the Virtus Lab company, it's probably due to the fact that we are the current steward of Scala, so the competition. Yeah, who is using Scala? People, okay, please do not throw the tomatoes for those people. Apart of that, we are doing some, as we are doing Scala, so we are pretty into the virtual machine stuff like that. We are doing pretty crazy stuff with tooling, like for example, model context protocol for the class path, because everybody is doing model context protocol. It's not the last time it will be mentioned this day. Also things for Bazel, monorepo, etc., etc. Me myself, I'm not involved in Scala at all. I'm doing the newsletter JVM Weekly, which is one of the media patrons of this conference, so I'm very pleased I had the opportunity. However, that's all the introduction I have, because I have 130 slides, 45 minutes, and I want to do the demo. So we gotta go fast. I know Sonic is not connected to Nintendo at all, however, it just fits the picture. Okay, because you know what we will be talking about today. We'll be talking about this little guy, Nintendo Entertainment System. So probably the first real console. And if you never heard about the Nintendo Entertainment System, and I don't know why you are here if you never heard about it, it is the one from the original Marios. However, for me, for years, I never heard about the console like that, because through my whole childhood, I have something like that. And it's my original console that my father bought in the '93. I still wonder if there is anything like that ever going abroad. And this is my original cartridge, because it's part of my childhood. Not the original NES, the so-called Famiclones. And they were quite popular in the Eastern countries. So never had the original NES, still wanted to know how that shit works. Because I was always into the mechanics of the emulators. That's probably the reason why I'm even tinkering with the JVM, because I always liked all those posts about the problems with the memory, processor, emulating of the old console. That's wonderful. It's a great read if you like it. And our story starts in the 2020. Because it's the time when world got crazy. Never got sane since this time, unfortunately. However, people had ideas and they have a bit more free time because we started to work remotely. And I decided, okay, if not now, probably never. So we decided, okay, it's worth to do the emulator for the original NES, because like I said, my first console. And never did that for the next 4 years, because in the pandemic we never had time like that. However, after the period, I decided, okay, it's time to get back to the original idea. However, I approached the problem from a bit different perspective. Because, it's not that you are creating the emulator from scratch. There are already a lot of good, interesting emulators on the market. So it's better to go through one, see what's interesting, and do it better. At least partially, because there's a lot of the technology and a lot of people work behind the emulators. So I took one that is called VNES. It's written in Java. Who likes Java? Expected that, because that's probably the funniest fact I learned during research for that presentation, that main boss of the original Contra is called the Emperor Daemon Dragon God Java. That's the original name for the original Contra. And VNES was not the best piece of code, due to multiple reasons. The first one, it's very old Java, JDK 1.8. Other thing is do not have build system at all. You are just compiling it. It is based on applets. And the code is very tangled. And the code is very tangled. The reason for tangled code, I learned it hard way why it was developed like that. However, still I decided I can do something better. So I would say last half of the year, I decided to create my own version, fork, that is fully rewritten in Kotlin. And now I will be presenting you the journey. Because the emulator KNES, that's how I called it, it's made in Kotlin, it has Gradle build, it has composed UI, and the code is modularized. However, it's coming with some limitations. Why? I will explain for you today. And for today, this is our journey for today. We'll go to the NES architecture, and that will be probably the longest part of the whole presentation. So if you expect that much Kotlin, there will be Kotlin. However, probably we'll more focus on NES. We'll be discussing why writing emulators is interesting and why it's such hard stuff. Also, what are the interesting aspects of doing that in Kotlin? Finally, wrapping up, why even do that? A part of the fact is interesting. OK, like I said, we do not have that much time. So let's start with the architecture of SNES. Nintendo and NES probably it should be pronounced NES. And it will be a very simplified example. If you want something deeper, there's wonderful blog post, NES Famicom Practical Analysis of Architecture. It's going very deep. I've stolen a lot of facts from it, contacted with Artur, so he knows that his samples will be presented there. And we'll need to start with the motherboard, because we'll be talking about the hardware now. That's how the original hardware, original Nintendo Entertainment System looks like. We'll start with the first piece. We'll start with the CPU. And history of the Nintendo Entertainment System CPU is quite interesting. Because first big 8-bit CPU used in the computers was Intel 8080. It was popular, featured in the first personal computers. It has 8-bit data bus and 16-bit address bus. It's exactly like NES will have later. However, probably even more important from the point of view of the consoles was Motorola 6800, which was totally different. However, it was the basis of the all further improvements. Next one was MOS 6502. That was a redesigned version of the Motorola. They stole the design and made it cheaper. Made it cheaper, not compatible, but cheaper, and that was fine. Apple was using it, Atari was using it, Commodore was using it, everybody was using that CPU. And Nintendo, and that's a very interesting fact, asked Ricoh to create something specifically for them 10 years later. Because they needed something very cheap for their console. They needed something that is already have the big market saturation. So they decided, OK, let's go with something that was already in Commodore, Apple, Atari, so developers will know how to use it. 10 years later. So when NES joined the market, it was already very stale hardware, and it is pattern that Nintendo is doing till this day. They learn that it's working. Other interesting fact is that, OK, maybe I will, because the license, there's no proof that Ricoh ever had license for using MOS. However, I do not want two lawyers here. There will be different reasons to have the lawyers during the presentation, so let's skip that part. OK, what 8-bit even means? Because it's very hard. Like we mentioned, this original CPU, oh, what happened? What happened? Oh, my God. Well, just today. OK, it's my fault. It's my fault. This time it's my fault. OK. So what 8-bit even happens? Bitness is a very hard thing to describe. Because, like we mentioned, the CPU had 8-bit, it had 8-bit register and 16-bit memory address space. So, but however, everybody agreed, OK, if it has particular kind of graphics, let's call it 8-bit. Also, this was the category of the CPUs. What's interesting coming with the 8-bit architecture is the fact that the biggest number that can be stored in the registers were 256. So whenever you have points like that, it's stored like this. So you need to have 3 numbers, or even more. OK, we are talking about the CPU. That's probably all the knowledge you need to have. Let's talk about this guy. Because creating sound for the old devices, OK, maybe just give us, let me talk, presentation, let me talk. Creating sound for the old devices was very hard. Because it wasn't working the way that you have some kind of the MP3 and you can run it. Because, that little guy had kilobytes of the memory. And cartridges has also kilobytes of the storage. So it's not possible to compress MP3 or any other thing to that level. That's why they were more using orchestra approach. So they had different channels for audio, and they were joined together for the interesting sound that is currently called the 8-bit sound. Let's start with the first one. This was pulse channel. There was also channel for a noise, so creating that interesting background. A triangle, and sample. So doing some pre-designed repeat of sound. That is not linear. Together, it could work like something like this. So original creator of NES could do magic with just those instruments. So that was the sound. And it was, okay, you will see how hard it is to implement that in Kotlin. You will see, I promise you. You are laughing, I did not. Okay, next thing, we have the VRAM. Okay, we talk about the CPU, we talk about the sound card. Now it's time, because it was a sound card. There wasn't any sound in that in truth. Okay, however, we will go to that. Now we are talking about, there's a bit of the memory. NES had 4 kilobytes of the memory, 2 kilobytes for the CPU work RAM, so the RAM of the CPU, and 2 kilobytes for the RAM of the picture processing unit, so let's call it GPU. Yeah. And now we'll cover that little part. Because we are coming to the interesting part of the NES architecture, because what we had there, it was quite simple. CPU, GPU, picture, sound card, and now it needs to see how it even worked in practice. You had the CPU was reading from the cartridge. So the thing that the game was delivered on was reading the program ROM. So what is the logic of the particular application? And then whenever they needed to draw some kind of the sprite on the screen, it was just using the other part of the cartridge, so-called character ROM. Simple, yeah? It will get interesting in a moment, because cartridges are black magic. You know, whenever we are taking we're going to store and buying the new version of Final Fantasy on our Blu-ray discs, this is for PlayStation, we have just data. CD, there's no calculation done, computation done on the CD-ROM. Most of the cartridges currently are also the glorious memory cards. Cartridges for NES, they were microcomputers. And those microcomputers were getting more and more powerful with each year, because the Nintendo Entertainment System was on the market for 10 years. And you can imagine how fast the technology was developing at this time. So this is the Nintendo Entertainment System cartridge for the original Mario, one of the first game. That one is for Zelda, Legend of Zelda. As you see, it's more complex. So architecture of NES is working in the way, okay, that's why we get from there to there. There is an improvement. And all that stuff, like I say, PG-ROM, character mappers, they are stored on those cartridges. However, okay, do you remember that picture I presented you a moment ago? It's just the half of the truth. Because on the cartridges, the problem with NES is that the half architecture is part of the console, and half is the part of the cartridge, because cartridge has something called mappers. And mappers were special bus that was allowing cartridge to do their own logic, switching the banks of memory and doing their own calculations. Rather than cartridge containing only the game program, that's the fix, it has a separate set of addresses and data lines that connects directly to CPU. So it's not only that cartridge is having logic, it was also directly connected to the particular piece of the hardware in the console. Let's imagine how to emulate that. And it was the standard, as it was just the standard of registers, it was changed, getting more and more complex through years. There are even special mappers for sound. So now it's time to explain why writing emulators is interesting, in that strange way interesting. First fun fact, there is no colored palette in NES. There's nothing like color in NES. Because, whenever you are taking the picture of the Nintendo Entertainment, okay, Super Mario Bros. In the Google search photos, as you are seeing, each of the picture has a bit different color. Why? Even when I was doing my emulator, I even achieved something like that, because I messed up some stuff. It's looking quite nice. I should present it to you. However, I achieved results like that. And the reason is quite simple. Because whenever we are talking about the modern cards, they are using digital signal. So whenever they are painting the frame, it's always the same. In the Nintendo Entertainment System, they were using some code Chint, and there is analog. Analog signal is never the same. To the level that this code RCA cables, they are using the radio signal to distribute the sound, distribute both sound as the video. There's even because in the US, there's some standard called NTSC, and it has wonderful extension called Never Twice the Same Colors. Because it was more. It wasn't like, you have particular color for particular picture. You are just saying, OK, we want that combination of luminance and color going that strong. However, that strong is subjective, depending on TV, depending on cable, depending on your state of your console, because it can get stale a bit. For example, not all transistors are working properly. So the NES didn't have a true combination RGB palette. It was using the combination of 16 brightness level and 12 hues. So theoretically, up to 200 colors. However, in practice, there were 64 numbers for the particular colors that programmers could use. And the colors are subjective, because there's yet another page about the development of the old consoles, called NESDev. And this one is trying to create the standard how emulators should behave. And there are multiple standards, varying with the colors a bit. Because, like I said, it was just the analog signal. We need to agree on something. So whenever we are having that in Kotlin, we need to load our palette. You have it on left. And you need to calculate what kind of the color should be used in particular pixel, based on the colors that we defined. So we are having wonderful color tables. Because, like I said, there's no colors in the ROM. We need to use something that we provide to emulator. Like I said, you can do crazy stuff like my Purple Mario. Next thing, emulating mappers is the worst. Because, like we already mentioned, mappers are interesting. But, in that Chinese interesting way. Yet another great example, Nicole Express. She is a French developer who is having the blog about the Nintendo Entertainment Systems. And this post is 1 hour long read. Because they were, I want to say to you, that many mappers, around 100. Each of them needs to have the separate way to emulate. Because mappers were working the way, like I explained, that they could do any black magic. Because, for example, they could do sound emulation. They could improvement. They could do, now we want to have the separate logic for each program depending on what is loaded on the screen. And they could control console in that way. They could have the different sprite sheets, because NES had limited, it had just 2 kilobytes of RAM. So whenever needed, cartridge could have additional RAM that was controlling what sprite palette is actually used. A lot of different things, including bank switching, transparent address space, things like that. And multiple different mappers, 100 of them. Each of them needs to have the separate class, needs to be emulated separately. And that is the problem with emulating NES. Whenever you have mapper, you need to have access to the whole hardware, because NES wasn't modular like our Spring application. With NES, everything was directly connected to everything. So we need to emulate that. For example, for that 100 of different, as we are talking about the Kotlin, C classes are very good for emulating that stuff because you need to have a different implementation for that particular object, and sometimes you need to use switch. You truly need. OK, so how do you know which mapper should be used? You know it because there's standard for that. And the standard was created, named interleaved NES, or simply NES Emulator standard. And in this, as we see there, header, we are reading what kind of mapper should be used. How much code it is, how much graphic it is in the file, which mapper to use, what mirror and battery features are expected. Because when you have the cartridge, it was the computer. It had logic on itself. When you have the stream of bytes, you need to emulate everything that is happening in that cartridge by yourself. This is example of, like I said, multiple mappers, mapper 0 nROM, so standard, MMC1, UX-ROM, CNC-ROM, Nintendo MS3. Compatibility grows as much as if you are adding additional mappers, you will have the better compatibility. And what's more, you need to simulate, for mappers, you need to simulate each of the registers because they were working like that. Now I will write some value to the particular register. You need to have that in mappers. Fortunately, like I had 100, so we have something to do. My emulator is supporting 2. Because that was the level I wanted to achieve. I wanted to play Super Mario Bros. Made it. Wanted to play Contra, made it, and call it a day. That's why, like mentioned from the repo, support only basic mappers will operate more in the future. Future is now. Still, I'm able to use run Super Mario Bros. As you will see. Hope so. 23 minutes, we have a good time. Fun fact 3. Emulator of sound is the worst, because it was the worst. Because emulating on mapper was hard, emulating of sort is even harder. Because let's remember, it wasn't just the single channel. It wasn't just the single thing to run. It was the whole orchestra of different sounds that needed to be emulated. And if you see, this is the slide shouldn't be there because it's in Polish. This is the first time I'm doing that presentation. So you have on the world premiere. Apple. So the problem is that Apple is a part of the CPU. Audio processing unit is a part of the CPU. And it was directly connected to CPU registers. They were stealing the frames they were stealing the computation from the CPU. Like you see there. We need to check, we are writing, there's no separate registry for the CPU, for the sound card, for the APU. It's using directly CPU register. And the problem is that, for example, it's some count stall cycles and stolen cycles. When APU, so our audio processing unit, was writing something, it was physically stealing the ticks from the CPU. It's not necessary anymore whenever we are doing that on the computer because we are not physically stealing anything, so we need to simulate that. We need to stop the CPU for a moment, decide how much we want to delay emulation, play the sound, and restart the processing of the logic, reading the opcodes. Freaking magic. Because, like I mentioned, in NES, everything is coupled with everything. That's why, when I originally stated that I wanted to write it from scratch, it wasn't the good idea, because specification is not the specification. It was analog. So every potential problem, every potential issue that happened in the original console, even unexpected one, but the creator of the specification became the standard. So I decided to use that logic from the VNES that I found, because there are already a lot of logic included in the internet. And this is very interesting. How can you test it if your emulator is emulating the sound properly? You cannot. So people from the most compatible emulator on the market, so-called Messen, are doing Audacity for that. They have reference recorded from the original NES, and they are comparing the output through the waves, not through some kind of tests. However, to make our life a bit easier, save states are super easy to implement, because I always thought that will be the hard part. Because, when memory, you need to preserve the state of the games. There are different games. Each of them can have a different way of storing that. And you know what? Maybe nowadays, when we have the complex games and we cannot just simply save 16 gigabytes of RAM every time we are making a save state. However, on NES, when we have 4 kilobytes, we can do it that way. We are simply, because, memory, we are talking about the code. Memory is an object. Object that simply can be serialized. So what we are doing in practice, whenever we are doing the save state, we are just taking all the memory object, stopping the emulation, then saving their state to the buffer, and restarting emulation again. And call it a day. That was totally surprising. However, there's still one interesting stuff, because stopping the emulation before saving ensures coherent, atomic, and restorable state without corruption to inconsistency, like capturing part of the state before a CPU instruction executes. So we do not want to emulate in the middle of the CPU instruction. Capturing another part of the PPU chain. So we don't also want to store the half-drawn image, because that would happen. We are just putting down, just serializing memory to the hard drive. Saving values mid update, for example, in the half of the frame render logic. Because we will get a consistency. Still, it's far, far easier than sound. It's far, far easier than graphic. So, audio IPU is freaking hell. Save state is something very trivial. OK, and there is one thing, because I already mentioned test. Fun fact, there are particular test ROMs that you can use, and there is a lot of them. Because, like I mentioned, every non-standard thing that happened in our analog system, it become a feature. Become a feature in the way that, for example, OK, if we are doing something wrong, the music sounds nice, OK, let's do that. And then, if you want to have, because, for example, something was not properly soldered in the cartridge, you cannot emulate that very easily. That's why, for each of the quirks, for each of the problems, for each of the games that needs to have additional compatibility, you have a test cartridge. I didn't use any. Super Mario Bros. That's all I need. OK, that was the domain, our most crucial logic. However, let's talk about a bit of Kotlin, because they were Kotlin samples. Let's talk about something that can be used for the UI, because picking the UI technology was very important. Original version I forked from was based on the applets. Compose was a good solution, because applets. Applets, whenever I see people talking about WebAssembly, OK, we'll have the bytecode in the browser. We had bytecode in the browser. It was cool. However, not that cool that I would want to use it anymore. So I decided, OK, the first thing, it should be done on there. The first thing, Compose, is a very good solution. However, the naive solution is working in the way that whenever there is change in the PPU, I'm simply redrawing the image, redrawing the whole picture using simply image. Fortunately, there are special libraries for that. The one is Skiko. It's the wrapper around the Skia. It's a wrap. OK, it's more complex, because Skiko is a Kotlin version of Skija. Skija is a Java implementation of Skio. Skio is the rendering engine for 2D graphics used by Google, Chrome, Flutter, and all the other stuff. So this was something that I used to make it work better, because performance there is quite important. We didn't want to have it sluggish. And I implemented one very sluggish version you will see in the moment. However, with the Compose, there comes some problems, because the first time I was using Kotlin multi-platform. And while Kotlin multi-platform is nice, it's not the perfect solution for them, because I thought, OK, I will be able to create version from the iOS, Android, etc. very easily. However, the fun thing, iOS problematic. Even whenever we are having the standard ways, libraries for that. However, it's doable. FileKit, very good. FileKit, very good library. However, I didn't expect one thing. You need to have the control. So it's not that easy, because currently, when I'm doing that on the laptop, I'm simply having the keyboard and mouse. This kind of keyboard. If I want to run on the phone, I do not have anything. So you need to have some additional logic included. It's not there yet. OK, let's go to the yet another topic that's probably the most vocal thing in 2025, because I expect we couldn't have the presentation. It's, again, the code of conduct of the conference, to have a talk on the conference in 2025 without mentioning AI. So yes, I used AI. I used it a lot, and I love it. Because it's not I was creating something from scratch. It's not that we do not know it's something very innovative to create NES. No, it's something that people were doing for ages. So all the AI engines had that in corpus. And it was pretty useful and allowed me to do it achievable in the, I would say, time slot I had for that. And for example, I used Juni. And you know what I learned about Juni? It's good, however, a bit slow. They are getting there. It should be better. Yeah. However, Juni was helping a lot, especially with Kotlin. Still, there are sometimes problems. For writing code, for getting the logic, it was good. For debugging, it is different kind of the tea, because that's probably the most hideous bug I had during the whole development. As you see, that's on the right, my output of the PPU. So I was drawing in on the picture frame, everything is nice. On the left side, I have just the first frame and black picture. And I was trying to solve it using different kinds of AI. For example, das Klein, using Cloud, DeepSeek, etc., etc. And he was doing that, OK, I'm calling the agent he, so they achieved that. Yeah, he was doing a lot of stupid brute force, synchronizing everything with everything. OK, if we have problem that on one side is OK, on the other not, synchronization problem. Everything, he was trying to synchronize just everything through code. OK, adding indirections. OK, let's do yet another layer. Changing UI logic. Adding manual ticking. So OK, let's force redraw for the picture, etc., etc. Drawing sample images to check if rendering was right. That was quite clever. And he was trying to do, we are going to the list in the loop. OK, if we get to the all items for the loop, let's start again. Maybe it will be working better this time. Probably there is some kind of the MCP that could help me, but it didn't. Yeah. This is, for example from ChatGPT. If this is the alpha, OK, because they said, OK, you have problem with alpha channel. And I have a question. If this is alpha channel, why word number in the right top corner is wrong? And he created the whole root analysis. Why is that? Totally made up. As you see, shifted, offset, read premature. It sounded very smart. You know what was the problem? You know what was the problem? That was two different objects. Simply, there were two different objects. I was rendering the wrong objects. And AI couldn't get it to the two different afternoons. However, there are kinds of the, and I did it when the first time I decided to attach the debugger, I found it in the spot. So sometimes AI is not good for everything. However, like I said, have you seen? It sounded very smart. Still, there are kinds of the errors. It was wonderful to work with, because we are talking about the Nintendo Entertainment System. And I get an error that, for example, my first level of Mario, I imagine you know how the first level of Mario looks like. Not like that. And I was saying that I was giving the prompt, I'm writing the NES Emulator, Super Mario Bros. Start at the word 0-1. What could be the cause? And interestingly, thinking model overthought the problems and was making up some different kind of the solutions. 1 minute of thinking, nothing worked. Non-thinking models got in the one shot. Because that was very popular error that already had in corpus, because we are talking about the NES. I'm not the first person who are doing the NES. A lot of people did. So it was well-known problem. Using non-thinking AI was simply better. because it didn't try to be very smart. The problem is that whenever you are having Mario is using memory very efficiently, so you do not store the whole level in that. You are just storing some references that it's mapping with the cartridge. If you have the trash in your memory, and I had objects that were not properly filled, I would say, it can do every in the different direction. They are yet another wonderful source, new retro game mechanics that you can learn a lot about the development of the old games. Oh my God, I probably did a lot of research for that presentation. Probably, hey, still love it, still worth it. However, it's time to explain why it's even worth to do emulators in 2025, why to make it mine. Because like I said, it's not some code that nobody written before. It's not very creative even. However, making it mine brought very interesting stuff. The first thing, I have control over it. This is the modularization. I would say original stuff was just a piece of garbage. Now I have the different. I was able to swap, move the components, the different kind of the UIs, different kinds of the controllers, made it modularized. This way, I'm able to switch the way I'm rendering stuff and controlling stuff. And I will give the first demo of today. Let's check if it's working properly. Let's move it there. I will try it. OK, do you see that? Do you see that? Because it's running. It's not on the slide. It's the running thing. OK, let's give me a second. OK, terminal here. Because when I had my problem with the debugger, I needed to somehow check if it's working fine. So I was doing the standard way of debugging. So I was rendering PPU to the terminal, checking if I will see any kind of the Mario. And give me a second, because I will. Oh my God. Do you see what is happening there? OK, let's do not kill my machines, because it's probably the most resourceful way to run Nintendo Entertainment System ever. It's hanging my computer. OK, let's get back to the presentation. Let's look for my screen. Because the original version was looking like that. And it was fine enough debugger. However, I decided, let's color that. I don't know why. I just wanted to have it. So we have ability to run the Super Mario Bros. In terminal. Why? Because we could. And that's the only reason I need. And the other stuff, OK, but we can do far more things. For example, have you heard about the experiment Gemini plays Pokemon? That LLM was playing Pokemon. OK, they were trying to learn LLMs to play the Pokemon game. The cloud failed, the ChatGPT failed. Gemini made it. So it's very strange thing that currently AI can play Pokemon and win it. However, I was originally thinking, OK, I will be doing version of LLM playing the Pokemon, playing the Super Mario Bros. Then I realized that having the latency of few seconds is probably not good for the Super Mario game's input. Still, I think one day I will use it for some kind of the RPG, for example, Final Fantasy, because I have externalized control. I can do anything I want. For example, and this is something I did once on the hackathon, because it's not the first time I was trying the retro mechanics, having the ability to have the mobile phone as a controller for NES. Because we can have a WebSocket server for that, and we can connect our mobile phone web page to the WebSocket, and we can achieve that everybody here will be will be playing Mario multiplayer. And if I will have opportunity, I'll probably present it next year on some kind of the lightning talk. Because it's totally doable. This is something I already did. However, the problem is there's one more thing that is very interesting. We have direct access to the memory. And by direct access to memory, like I explained, we have retro games mechanic explained. We can do strange ability. There are some kind of the bugs that are making Super Mario Bros. Work strange. We have memory object. We know what kind of, because people already decided what kind of garbage needs to be put in the memory. We can put that garbage. And we can have our Super Mario strange world generator. There are true pictures. OK, and the last thing, OK, and that's probably things about the interesting stuff we can do. There's one yet interesting, not that well-connected stuff to the topic of the presentation, however, still interesting, creating the ROM hacks. ROM hacks are the different version of the well-known games, changing just a bit of stuff. And currently, there are a lot of different editors just for that allow us to change the sprites of Mario, that are allowing us to do some heavy magic with the levels. For example, change the way that logo on the first scheme is looking like, changing the structure of the levels. And maybe not a lot more. I think there's also ability to write. There's special, OK, but probably not connected. I shouldn't put it in the presentation. There is also the NESFAB language that is currently can be used, high-level language, just to create the NES application. We have 4 minutes. So I achieved that. I have some time. And now I will do something very, very illegal. Because I was talking about the NES emulator. I was talking about the Super Mario Bros. Probably it's time to show it to you. That's the reason why I have cartridge with me, because I can say I dumped it myself, and that's legal. Because I do not want to pay $2.5 million just for having the show on the Kotlin Conf. Still, it's worth to try. Because now, what we will do, and oh my God, it will be hard, because I have a different screen than you. Can we switch the, OK, what can we do? Because we have 3 minutes. OK, I will try to do that. Because you want to see the emulator. So I need to give it to you. It's not terminal. And I'm doing that on the other screen. That's why it's such a pain. OK, have it. Need to move it to the other screen. Yes, it is. We need to load the ROM, because I have one totally special ROM for that occasion. I was talking about the ROM hack for a reason. So now it's time for a question. I have 2.5 minutes, so I won't be able to win whole Super Mario Bros. Because it's physically achievable in the 5 minutes. However, I will try to do that as far as possible whenever you will have some questions. So please ask me anything. Thank you for the presentation. And please feedback. And if you have a bit of time, please give a feedback, because I would love to have it. Like I mentioned, it was the first time I was presenting that. In my imagination, that was much fun than that. Much more fun than that. I hope you still love it. It's fully rendered by Kotlin. It's fully drawn in Compose. If you want to just check the emulator itself, there is a QR code for that. OK. Thank you very much. I just want to have that little picture. OK. Oh, freaking God. Let's do that. OK, I have 1.5 minutes. We can go. OK, OK. Made it. OK, probably we'll just end it that way. However, I can truly win the whole Mario on the 3 lives. I'm good at that. I'm doing that for the 30 years.